In this video, I'll be discussing about valence bond theory or VBT. From valence bond theory, we come to know certain characters of the complex or compounds, like the color, geometry, and magnetic properties. Moving on to the assumption, the first one is center metal atom. The center metal atom or ion of the complex makes available a number of empty orbitals for the ligands to form coordination bond with the center metal atom. Here, suitable ligands, they form coordination bond with the center metal atom, and the number of empty orbitals is equal to the coordination number of the central metal atom. The second one is the hybridization. So the appropriate atomic orbitals of the metal, they hybridize to give a set of equivalent orbitals of definite geometry, such as square planar, tetrahedral. Say for example, if the hybridization is sp3 hybridization, then it will give a structure or geometry of tetrahedral. If it is dsp2, it will give a structure of square planar. The geometry will be square planar. So accordingly, this is for the coordination number 4. This is also for the coordination number 4. Say all total 4 orbitals are hybridized. That is 1s and 3p's. Here 1d, 1s, and 2p's. So the coordination number is 4. If it is for coordination number 5, it will be sp3d. sp3d. It will be trigonal bipyramidal. And if it is for coordination number 6, the possible hybridization will be d2sp3. Here the inner d orbital is hybridized and the other one is sp3d2. This is for octahedral. Octahedral can be of two types. One is where the d orbital is the inner d orbital and the other one is the outer d orbital. The next one is the inner and outer d orbital. The third one. Here the d orbital involved in the hybridization can be either of the inner d orbital or the outer d orbital. If it is for inner d orbital, then the hybridization will be this. If it is for octahedral, it will be d2sp3, and if the outer d orbital is involved in the hybridization, then it will be sp3d2. Next one, each ligand has at least one lone pair. Now all the ligands that are coordinated or that are forming coordination bond with the central metal atom or ion, they will at least have one lone pair to form coordination bond with the central metal atom. The fifth one is the empty hybrid orbital overlap with filled orbital of the ligand. That means the empty hybrid orbital of the central metal atom will overlap with the filled orbital of the ligand. The next one is effective atomic number or EAN. It is the total electron possessed by the central metal atom and the electrons gained from the ligand. So for example, the first one, the second one you do it. Here for the first one, the EAN equals to the total number of electron present in iron is 26, which is the atomic number, plus each of the Cn contributes 2 electron. Therefore 6 is the total number of ligand into 2, that is equals to 26 plus 6 to the 12 equals to 38. So the EAN for this particular complex is 38. You find out in the same way you find out for this one. Let us see one of the application of valence bond theory. Let's consider the octahedral complex, that is CrNH3 whole 6 with a net charge of +3. Okay, here the oxidation state of the center metal ion is +3. Okay, that is x plus 6 into 0 equals to +3. Therefore, x equals to +3. Okay, so that way we get the oxidation state of the center metal ion. Now, we know that the atomic number of chromium is 24. Therefore, electronic configuration of chromium can be represented this way. Okay, since the hybridization is involved only with the outermost orbital, therefore we shall consider only the outermost orbital. Okay, so we can write 3d5. Okay, we can write 3d5 4s1. Okay, now let's do it this way. Okay, this is how we do it. 3d, it has 5 orbital. Okay, 5 degenerate orbital, then 4s 1 orbital, and 4p also we put it. Okay, now for chromium in the 3d orbital there are 5 electrons, so we put 5 electrons. Okay, we will follow Hund's rule. Okay, first we will fill it singly for all the degenerate orbital, then only if there are any electrons left, then we shall fill it in the opposite spin. Okay, for 4s there is only 1 electron. Okay, now we know that we have calculated the oxidation state of chromium +3. Okay, so what happens here, 3 electrons will be removed. Okay, so from the outermost orbital, that is 4s, 1 electron will be removed, and from the d orbital 2 electrons will be removed. So all total 3 electrons are removed. Okay, so now we are left with this one. Okay, in the 3 orbital 2 electrons are removed, so only 3 electrons are left, and in the 4s the electron is removed, so no more. This is how we write. Okay, now in the complex formation, okay, we have the empty orbitals, that is 2 3d, okay, 2 3d empty orbital, 1 4s, and 3 4p orbitals are there. Okay, so all these empty orbitals, they hybridize to form, okay, they have hybridized to form d2 sp3 d2 sp3 hybridization. Okay, so there will be all total 6 d2 sp3 hybrid orbital. Okay, now for the complex formation, okay, for the complex formation, all these empty orbitals, okay, which are of d2 sp3 hybrid orbital, will be filled with the ligands NH3. Okay, NH3, these electrons are there, and here also it is NH3. Okay, and here NH3. Okay, this is it. Now, since there are 3 unpaired electrons in the 3d orbital, therefore the magnetic property is paramagnetic. Okay, so paramagnetic means if there is any unpaired electrons, okay, then it will be or that complex will behave as paramagnetic. And since it is forming 6 hybrid orbital of d2 sp3, therefore the geometry is octahedral. Okay, so let me give you one problem. Okay, you try to solve it by yourself. That is CONH3 6 3 plus. Okay, you try to solve it for this one and let me know. Okay, whether what kind of magnetic property it is, and the hybridization. All right. So now discuss some of the limitations of valence bond theory. Okay. So there were more than 3 limitations, but I shall be discussing mainly on the 3 types of limitations. The first one is it failed in distinguishing between the weak field and strong field ligand. Okay, that's why it could not give any explanation on whether that particular complex will undergo an inner d orbital hybridization or outer d orbital hybridization. Okay, the second one is for the coordination number 4. 2 types of structure that we can have is one is square planar and the other one is tetrahedral. Okay, for square planar it undergoes dsp2 hybridization, and for tetrahedral it undergoes sp3 hybridization. Okay, but since in both the geometry all total 4 hybrid orbitals are involved, and therefore it could not give any detailed explanation about that. The last one, that is magnetic properties. Okay, here we have 2 types. If it is unpaired electron, if it contains any unpaired electron, then we call it as paramagnetic. If all the electrons are paired, we call it diamagnetic. Okay, but it could not give any detailed explanation about that, so a valence bond theory failed in those things. Okay, there is one more thing that I would like to mention, okay, before ending this one. In order to calculate the spin magnetic moment, okay, spin magnetic moment, or we just write Bohr magneton equals to magnetic moment, okay, equals to root over on to the next one. I just would like to give you a formula, that is to calculate the magnetic moment. Okay, it's actually spin magnetic moment, so the unit is Bohr magneton. Okay, the formula is root over n into n plus 2. Okay, where n is the number of unpaired electron.